Okay. Is this one? Okay. I'm supposed to use the mic because of the recording. Told me to use it, so I'm using. So welcome back from tea. So we have 3 talks in this session, 25 minutes each, with 5 minutes for questions and changeover. And our first speaker is Sarjick Bakshi, and his affiliation was Center for Excellence in Basic Sciences, but it has changed to IIT Kanpur recently. And he's going to speak to us about G vectors.
Thank you very much for giving me this opportunity to talk. I actually come from the Lakshmi Sheshadri School of Standard Monomial Theory, but today it's a cluster algebra talk. So I'll talk on this joint work with Professor Bernhard Keller. Yeah. On G vectors of Plücker coordinates. So it's really him like who got me into cluster algebras and categorification. He was like very generous and patient, like, with his ideas and problems. So okay, I don't understand. So let's. So maybe I'll just use the computer. This seems to be not going scrolling properly. So anyway, let me continue. So in the morning, Evgeny introduced Grassmannians, and then Lara introduced mutations, cluster algebras. So this is a talk which combines both. So let's go briefly over the definitions. So we already know what mutations are. So for mutation, you need a quiver and a seed and certain variables. And the quiver mutation was defined with these 3 rules. If you have an oriented path, then add an arrow, reverse all the arrows, incident to K, and remove all the maximal set of disjoint 2 cycles. And there was an algebraic relation, like, which is called the exchange relation, where you mutate one variable. So the initial seed is the seed we really start with, and the cluster is the n tuple u bar which appears in a single seed, and the entries of u bar are cluster variables. The cluster algebras is the Q subalgebra of the field of fractions defined by is the Q algebra generated by those variables. And if there is a mutation equivalence between 2 quivers, then the cluster algebras are isomorphic. So this was Fomin-Zelinsky's first paper. And then they saw that, like, if you take some varieties coming from geometry, their coordinate algebra seemed to have some cluster structure. So they had to improve the definition of this quiver. So they introduced what's called ice quivers. And the point of this frozen vertices is like they will appear as coefficients. So you cannot invert them. So an ice quiver is basically a quiver which contains a subquiver which we declare to be frozen vertices where we don't mutate. And a cluster structure on an affine variety is basically giving a quiver and an isomorphism of the cluster algebra tensor with C with the coordinate ring of the cluster algebra. And can you read in the bottom? There is some issue. I am a bit confused about. I don't know how to fix it. I really don't know how to. Now the bottom can be read, right? Yeah. And one of the first examples are these examples motivated by like Lakshmi Sheshadri School of Mathematics, like Grassmannian flag varieties, partial flag varieties, and so on. So, and yeah, Professor Scott is one who gave the cluster structure on Grassmannian or an arbitrary Grassmannian. So it was okay. So let's start with the question. So we are interested in something called G vectors. So G vectors are computationally less heavier than these cluster variables. But to define them, we occasionally need something called C vectors, but one can do it just using quivers. So for that, one defines a framing of a quiver as you just add two frozen vertices as shown here. And then you call a vertex to be green if there is no arrow from this j prime to I, and red if there is no arrow from I to j prime. And Dirksen, Wyman, Zelinsky in their fundamental paper have shown that every mutable vertex is of a framed quiver is reachable from which is reachable from Q. There is a typo hat is either green or red. So this is really the sign coherence of the C vector. So that is what they proved using quivers with potential. So for example, we start with these green vertices, then we add a framing, and then we mutate at 1. You see, like the vertex 1 becomes red, and we mutate at 2, the vertex 2 becomes red. So really, like we can color all the mutable vertex. So this allows us to define something called G vectors. So in the initial seed, we declare the G vectors of the cluster variable to be the standard basis. And then we define a mutation rule, very much like what we define for cluster variables. So it's really mutating at one vertex. So, and in every other vertex, the G vectors remain same. It's like minus GKT plus the summation of GIT, where K is for all the vertices K to I, and if K is green and if it is red, it's from I. So let's T naught. Okay. So it's once you can encode the data of this cluster algebra in a tree, like you start with the initial seed, mutate at a vertex. It's a like n regular tree. So then you move to TR is a R regular tree which encodes this cluster data. So you start with an initial vertex, you go to some mutate at some vertex, and then you just go on. So for example, let's work with this. So the G vector in this initial series like E1, E2, E3. And then once we mutate at 1, the first variable becomes like minus E1 plus E2, E2 and E3, and so on. So you can see. So okay, this is a green to red sequence. There is more story in it, but we'll not get into it today. By the way, like all these mutations can be conveniently done using an app developed by Professor Keller. So maybe if we have time towards the end, we can just see how it works. So we are interested in the Grassmannian. So as Evgeny described in the morning, this Grassmannian comes with a God-given embedding called the Plücker embedding, where a k-dimensional space is sent to its k wedges. And if we take the standard basis, and like we know the basis of the k wedges of a vector space, and Plücker coordinates are basically dual to those bases. And the coordinate ring of Grassmannian is generated by these Plücker coordinates. So this coordinate ring has been cluster structured by Kumar Zelinsky in their third paper, I suppose. And then for arbitrary K, the cluster structure was shown by Professor Scott. And then using categorification by projective algebras, a cluster structure was given by Guy Schlechter Schroer. It's basically you have to give a quiver. That's the point. So let's so for example, if we take 3, 7, so this is the quiver we have. So you see, like we cannot mutate on those blue vertices, but we can very much mutate on the green vertices. And this quiver is also obtained from Taylor's mutation app. Yeah. And there are few observations, like you can see, like it's not all Plücker coordinates which has appeared in this seed. And all like there are more Plücker coordinates than what has appeared here. So the question we are interested in is, like, what are the G vectors of these Plücker coordinates? So first, like Plücker coordinates are indeed a cluster variable that was shown by Postnikov and Scott. And so this is, I believe, Geist-Richter square seed. It's mutation equivalent to the seed by Scott. So as I mentioned, like we are interested in the G vectors of the Plücker coordinates. So for that, we go back to a description of an association given by Lakshmibai and Wyman. So they were interested in finding the singular locus of Schubert varieties in Grassmannian. So I was lucky to learn this from Lakshmibai herself. So the idea is this, like if you just take something like index 357, so the Plücker coordinates are indexed by this set IKN, which was like and then you subtract one from here, subtract 2 from here, subtract 3 from here, you get a Young diagram. Yes. So this is the Young diagram we are interested in. And if you use Taylor's mutation app to find the G vector of say 357, you will see like this becomes like something of this. So it's like this plus this plus this, and you subtract this portions which comes in between as values. Four plus and you subtract. So we experimented and we found that indeed, like there is a pattern. Like these are the G vector, these are the vertices which appear in the quiver. So this is experimentally verified. Now we need a proof. So this is precisely the statement. So the G vectors, like if you denote them by peaks, like in Russian school, you can draw Young diagrams using like some mountains, and then you can define some peaks and valleys. So it's like you take the G vectors of the peak, the basis vector for the peaks, and subtract the basis vector for the valleys. So this gives the G vector. Yeah, so this is in the this is in that cluster, Plücker cluster we drew. So if you wish, like it's in the Gothenburg group of FT, so the sums of the. Okay, so this is the statement, and now we need a proof. The proof goes via categorification. These are the peaks and the valleys. For example, like you have the peaks at these vertices. So you can draw this Young diagram just like the Russian school would draw. And then the valleys would be the one which comes between two mountains. Yeah, so this, the Plücker coordinate correspond to these indices correspond, like is there in that quiver. So I need G vector for any Plücker coordinate. So this is my Plücker coordinate. So my Plücker coordinate has been transferred by this Young diagram. So this is my Plücker coordinate, and these are the one which appears in the quiver. So once we do this mutation, once we use this app or like try to find this G vector by hand, we can see that the G vector turns out to be like this. And Now we need a proof for this. So the proof comes by the categorification. So let's go back, let's go to the language of categorization. So C is 2 Calabi-Yau category if it is Hom finite and there is a bifunctorial isomorphism between the Hom of xy with the Hom of y and sigma square x. Sigma is the suspension functor or a shift functor in a triangulated category. And an exact category is Frobenius if it has enough projectives and injectives and they coincide. Then Happel really showed that the stable category of a Frobenius category is a triangulated category. And C is stably 2 Calabi-Yau if it is Krull-Schmidt and the stable category of C is 2 Calabi-Yau. And a cluster tilting object is a basic object such that basic means the direct sums, it can be written as sums of indecomposables with multiplicity 1. T is rigid, that's first extension vanishes, and for all object satisfying x1 t x0 lies in at t, where at t is the direct summons of finite direct sums of copies of t. For a cluster tilting object, qt denotes the quiver of endomorphism of t. So really, like this is the thing. So once there is this quiver for an acyclic quiver for type AN, this cluster categories were defined by Caldero, Shepperton, and Schiffler, and then Buan, Marsh, Reneke, Todorov defined it for any acyclic quiver. It is defined as the bounded derived category of the module category of algebras by tau inverse sigma, which is like. And Keller proved that this category is triangulated, and Yama Yoshino did it for like, so they generalized the definition for 2 Calabi-Yau categories. And for ice quivers, it was, the categorization was first done by Buan, Yama, Retin, and Scott. So this, under this correspondence, this cluster variables corresponds to rigid indecomposable objects. The clusters are cluster tilting objects, and the G vectors are indices. So we are interested in the G vectors. So it's like you have certain variables, U1 to U1, and then you associate some direct sum. This sum is a cluster tilting object. To each variable you get an indecomposable, and then you mutate. Say, for example, if you mutate at some t, you get like t k star. So this is really the correspondence which is happening. And this x between t and tk star, so if you want in this exact sequence form, is really one dimensional. So this kind of gives the correspondence. Now we are interested in G vectors. So whenever we have a stably 2 Calabi-Yau Frobenius category or a so stable to, it's like C, you have acyclic quiver, and then you start with the Frobenius category and you have the stable category. So you get the information of the Frobenius category, which is per se not a Hom finite category, from a Hom finite category. So that's the trick. So this is like adding coefficients. So Taylor-Retin showed that for every x in this stably 2 Calabi-Yau Frobenius category, there is a conflation. Conflations are like exact sequences where T0 and T1 belongs to at T. So this is like a projective resolution in loose words. So once you have this conflation, one can define an index in the split Grothendieck group of at T. Remember, note that these conflations might not be unique. Like for example, you can have these two triangles, or like 0. This is like some trivial example. So these are two conflations of 0. But if you look at the Grothendieck group and look at the difference of these objects, they remain to be unique. So one defines the index as the difference of these classes of T0 and T1 in the split concentric group. So in 2007, Professor Keller-Dehi categorified this index for a two-Calabi-Yau category, and it was also done by Keller for principal coefficients, and we generalized it for two-Calabi-Yau Frobenius category. So it's basically building on the results by Keller-Dehi. We had to modify it accordingly. It says that this ind basically categorifies the G vector. It means whenever you take a rigid indecomposable object which is reachable from T, the image ind is the G vector. So now we know how to get the G vectors using exact sequences. So that's precisely the idea. So all we need to get hold of a category which is like Frobenius category, which is nice enough, and some objects which we enough. So for that, we go to Janssen-Kingshu's paper. So we start with a completed pre-projective algebra of type AN-1 tilde. It's basically a circular graph, and you draw arrows in the other direction. So it's like a double cube. So we have this relation. Yeah, we have. I'm audible, right? Yeah, so we have these relations which are like xy is yx. For example, you can see like at this vertex, you go x and then y, and you go y and then x. So they are same, and you add certain more relation, like if you take x power I and pi power n minus. So for example, x cube and y4 in that direction. So they also have to be same. So this algebra is the pre-projective algebra is Noetherian of global dimension 2. However, B is only Noetherian. It's an infinite dimensional algebra, in fact, of infinite global dimension. Now define the Cohen-Macaulay category of B as the set of finitely generated B modules for which xi is 0 for I greater than 0. So Janssen-Kingshu have shown that these are same as the B modules which are finally generated free over the center, which is much more tractable, which is the power series ring in one variable. So let's see like how much we have extracted. So CMB is a Frobenius. So these are all shown by Janssen-Kingshu. One should really say that it builds on work of Geisler-Schreier. So Geisler-Schreier came up with this sub QK category. Like they build this pre-projective algebras, and Janssen-Kingshu's category is like they're related. Right? There is a map from CMB to sub QK. So you just quotient by the projective at n. So CMB is a projective category, a Frobenius category with projective injective, the projective B modules, and its stable category is a two-Calabi-Yau category. And CMB admits the cluster tilting object, which is direct sum of all this LIs. So LIs are certain rank 1 module, which will come very soon. And this I belongs to this Plücker cluster. Plücker cluster is the indices which has appeared in the 2 more minutes. Okay, which has appeared in the quiver, and this LIs really corresponds to this Plücker coordinates. So one can draw this LI using this diagram. So this was a recipe shown to us by Janssen-Kingshu, and you can see like if you have x, so the action of x is like x goes from I to I plus 1. It's multiplied by t if I is in I, or else by 1. So it's like 0 and 7 is identified. So we are working with the circular quiver, no? So the 0 and 7 are identified. So it's like a cylinder. And then we draw this diagram. So really you see, if you just look at this diagram, you see you can extract out a Young diagram in the sense of Lakshmibai and Wyman. Like you can see like this. This gives a Young diagram here. This is precisely the Young diagram for 357. And then once we use the conflation suggested by Taylor, which we have used in our paper, it shows that there is a map from the, so it's like there is, okay. So yeah, it's, if you, the direct sum of the peaks surjects onto this module, and the kernel is precisely the direct sum of the values. That's the idea. Okay, so on memories of Lakshmi and Sheshadri. Thank you.
Thank you, Sarjick. Any questions?
Thank you. So did you also consider, or what happens when you change the initial seed to another seed of Plücker coordinates?
Yes. Yeah, that's, so for example, we tried working with this square seed, but yeah, we didn't get hold of anything. The combinatorics is very messy. It would be nice to